In this lecture, we want to consider smaller exoplanet systems, in particular water worlds, or planets like the Earth that are hosting water and, of course, potentially biology. We start with the idea of ice giants. These are the massive planets that are not quite at the level of the gas giants of Jupiter and Saturn, but more similar to the other gas giants in our outer solar system, Uranus and Neptune. These are at frigid distances from the Sun in our solar system, distances of tens of astronomical units. Remember, Jupiter is about 5 astronomical units, Saturn is about 11 astronomical units. So we're talking about 20, 30, and 40 astronomical units from our Sun, or in the case of an exoplanet, from the parent star that's also a Sun-like star. These ice giants, as we'll now refer to them, are composed of heavy volatile compounds with freezing points above 100 degrees Kelvin. They do have gas giant atmospheres, typically hydrogen and helium, like the composition of the Sun and the atmospheres of Jupiter and Saturn. Only about 30% of the ice giant exists as ice. Most of the atmosphere is in a bizarre physical state called a supercritical fluid. There are a few or a small fraction of heavy elements in such planets, heavier than hydrogen and helium, and these include the most abundant elements beyond that in the periodic table: oxygen, carbon, nitrogen, and sulfur. And some of these elements in their compounds give the coloration to the gas clouds of these giant planets. About 20% is hydrogen and helium by mass. Remember that in the gas giants Jupiter and Saturn, the percentage that's hydrogen and helium is more like 90%. The first ice giant exoplanet was discovered quite recently, in October 2014. It's about 25,000 light years away and 4 times as massive as Uranus. It orbits its star at nearly the same distance as Uranus is from the Sun, and it's in a binary system in the direction of the Sagittarius constellation. We see 2 stars, one 2/3 the mass of the Sun and the other 1/6 the mass of the Sun. After this first discovery, others were discovered, and a phenomenon became to be called mini-neptunes. So there are 2 categories of exoplanets that, as the statistics came in, started to be dominant categories of planets. One are the mini-neptunes, which are, as the term implies, like our Neptune, but maybe slightly smaller or less massive. And the other are super-Earths, which, as the term implies, are like our Earth, only slightly larger or slightly more massive. This distribution shows, as Kepler started doing its work and was able to find the smaller exoplanets, the distribution is no longer smooth. There's actually a peak corresponding to a few times the size of the Earth. Remember, Kepler is measuring transit, so measures size and not mass, but we can infer they are also more massive than the Earth. There's a peak at a few times the mass or size of the Earth, which corresponds to a super-Earth, and then there's another peak further out, and these are the mini-neptunes. And then there's a long tail towards Neptune mass and beyond. In this distribution, it's clear that Saturns and Jupiters are actually quite rare. So the bulk of the distribution is in the form of mini-neptunes. It's quite an abundant and common category of exoplanet. Both types of exoplanet are classified by the upper mass limit of 10 Earth's mass. Mini-neptunes, also called gas dwarfs, are believed to be similar in composition to the ice giants Uranus and Neptune in our solar system. Super-Earths are believed to be rocky planets similar to the Earth in composition, with slender atmospheres and rocky bodies filled with silicates and metals. Let's look at the mini-neptunes a little more closely. This is a hypothetical cutaway of what the internal structure of a mini-neptune might look like. We can see the upper atmosphere and the cloud tops, the atmosphere with mostly hydrogen, helium, but also methane, ammonia, other gases and compounds, and then a solid mantle, which is including solid materials, but also frozen ices and gases, so water frozen as ice, ammonia and methane also frozen as ice because of the large distance from their star. These are very cold planets. And then a core, which is a mixture of rock and ice. It's very unclear what the composition of the core actually is. The core of a terrestrial planet is almost pure metal, but in these cases we think it's a more equal mixture of rocks and metals. it's possible that these planets in their interiors have liquid oceans, where they're liquid not because of the temperature, it's really too cold for a liquid to exist, but because of the intense pressure that forces gas into the liquid state, even at a cold temperature. So these are very bizarre physical objects. Now, the inference here is of the internal structure. This is based on models of these planets. We've not yet verified that these are the internal structures. Meanwhile, we have increased steadily, especially with the Kepler mission, the number of examples of mini-neptunes. One good example was Kepler 11f, discovered a few years ago. Has a mass of just over 2 times the mass of the Earth, but a density roughly the same of Saturn, which means that it's a gas dwarf with a hydrogen, helium, or water vapor atmosphere and just a small rocky core. Another example is Kepler 138d, which is even less massive and is thought to be a gas giant because of its low density. Mini-neptunes are far from their parent star, so they're at large orbital distance. That and their small size means they have extremely low temperatures. What about super-Earths? This is an exciting category because it obviously means they're cousins of the Earth. And we know the Earth is the only habitable planet in the solar system that we live in, and it's the only habitable planet so far that we know in the universe. So finding cousins of the Earth is clearly very exciting. Models provide different composition ideas for how their density is arranged, because these are not all the same kind of planets. A first point that should be made is just as our solar system has no hot Jupiters, yet they were some of the first systems to be found beyond, our solar system has no super-Earths. The terrestrial planets include 2 small objects, Mars and Mercury, and Venus and the Earth, which are very similar in size and mass. There is no super-Earth in our solar system. So once again, the rest of the universe is providing us examples of a new type of planet that we have no counterpart of or no knowledge of just looking at our own solar system, just telling us that the universe has plenty of things still to show us. The model suggests that some of these super-Earths are very low density and probably made of hydrogen and helium primarily. And that means they're more close to being a mini-Neptune than they are to being an Earth like our planet. Then there are intermediate density super-Earths, which either have water as a major constituent, and so are water worlds, or have a dense core shrouded by a gaseous envelope, making them like gas dwarfs. And finally, there are higher density super-Earths, which are likely to be rocky or metallic, and they may have a slender atmosphere that we can't measure yet. And these are the most like the Earth or the rocky planets of the solar system. So super-Earths can sit in different stages of differentiation. It's definitely theorized that super-Earths, especially the higher density ones, are going to have significant geological activity. Because remember that in our solar system, Mars corresponds to the threshold of geological activity. Mars has clearly been geologically active in the past, but is mostly geologically dead now. The Moon and Mercury, smaller still, are geologically dead. So we think the Earth and Venus are above the boundary for geological activity. And if you have yet more mass, as in a super-Earth, then you have sufficient internal heating and internal mass and energy released by radioactive decay that you're almost certainly going to drive geological activity and plate tectonics. And geological activity has been associated by astrobiologists with the potential for life. The dynamism of a geologically active planet creates more possibility for chemical reactions and the possibility of pathways to biology, something we'll discuss later. So having geological activity in an exoplanet is interesting. It makes it similar to the Earth, and it probably raises the probability for habitability in some way. Super-Earths are more massive than the Earth, and in the models, that suggests their crust would be thinner in proportion to the interior stresses. And the crust is subject to a stronger influence from the interior of the planet. So this all speaks to large amounts of geological activity and volcanism, of course. There are many examples of super-Earths now. The first was discovered just over a decade ago around the Sun-like star Gliese 876, and it was 7.5 times the mass of the Earth and had an orbital period of 2 days. That's stunning. That's 2 times faster even than 51 Peg. incredibly hot super-Earth, far too close to its star for liquid water to exist. So the first super-Earth was interesting, just the discovery itself, because until then nothing that small had been found, but it was far from being a twin of the Earth or a habitable planet. A few years later, by the mid-2000s, the first super-Earths with the potential for liquid water were discovered. In other words, these were super-Earths where their distance from their parent star was such that the surface temperature was within the range where water is a liquid, between the freezing point and the boiling point of water. That means technically they are habitable. So this is an amazing threshold in the exoplanet discovery. A decade after the first was found, we started to find exoplanets that were similar to the Earth, cousins of the Earth, and potentially habitable. And since then, more of these examples have been found. Perhaps the most exciting so far was only found a couple of years ago, and it's the exoplanet Proxima b, 1.3 times the mass of the Earth, orbiting the star Proxima Centauri, which is of course the nearest star system, less than 4 light years away. So here we have an Earth-like planet around almost the very nearest star you could possibly find, meaning it's easy to study, can be studied with small telescopes, and people have been gathering data for a while now trying to understand if this planet is habitable too. The answer is not yet clear. So now, a decade after the first super-Earth was found, many Earth-like planets have been found, literally hundreds. After finding hundreds that look like Jupiter, we've now found hundreds that are super-Earths, and eventually, with the sensitivity of Kepler, hundreds that are within a factor of 2 of the Earth in mass or in size. For example, Corot 7b, found several years ago, has a density close to the Earth. But there are differences. It orbits its star in an incredible 20 hours, which is actually the fastest exoplanet orbit yet. That is so close that its rocky surface may be molten, so very far from being habitable. So not all of these planets are habitable. Not all of them are hospitable. They have very different orbits. But it's exciting to see such different exoplanet architectures. And with the existence of Earth-like planets now confirmed many times, astronomers are confident that with time we will discover twins of the Earth. As we speak, no clones of the Earth have been found. And of course there will always be slight differences. And there's not quite enough data yet to tell if they are common or rare. Part of the reason for this is the full census of Kepler observations has not been completely analyzed. Kepler finished its primary mission a couple of years ago, and it took long enough data, nearly 5 years worth, to technically find Earth-like orbits, which is to say 1 year, and planets that were in the habitable zone of their sun-like star. But it needs the full Kepler data set to be fully analyzed, down to the sensitivity limit possible, to put a number on how many Earth clones are actually out there. We expect that analysis to be done soon because it's been ongoing for a while. The current record holder is very close to the size of the Earth. And in fact, by the Doppler method, there are planets that are close to the mass of the Earth, and by the eclipse method, there are actually planets smaller than the Earth. The record holder, I think, is currently very close to Mars size from the Kepler detection. So there's no question of Earth being a minimum mass of exoplanets that can be detected, and we can expect more of these in the future. We had indications of this being the case early in the exoplanet hunting game. Here's a distribution of the mass of exoplanets from the first 7 or 8 years of data, when there were only a few hundred exoplanets known. What you're seeing is the number of planets against the mass of those planets by the Doppler method. Notice that the mass measured by astronomers is multiplied by the sine of the inclination angle. And that's because the Doppler method detects the component of the planet's motion, or the star's wobble, in the plane of the sky, to or fro. If the planet was in a transverse orbit, such that we were looking straight down onto the orbital plane, there would be no Doppler motion, because all of it is transverse to our line of sight. And so the mass we estimate is multiplied by the sine of the inclination angle. Now that's a big uncertainty, because we don't know the inclination angle. Exoplanet systems are distributed randomly, we think, in 3-dimensional space at uniform inclination angles, but for any particular system, this I, the inclination angle, is an unknown. So we don't actually measure its mass. We measure m sine I, where I is unknown. However, it's okay, because as we do statistical work and just assume that the planets are randomly oriented, we know that on average, averaging over a sine curve over all inclinations, we will underestimate the mass of all planets by a factor of 2. That's inevitable. That's just due to the uncertainty of the inclination, but it means we're not going to be very far wrong in statistical sense. And what was seen in this distribution is, of course, that even when we only had the sensitivity to measure Jupiter over here, we saw this rapidly falling distribution to large masses, so things more massive than 10 times Jupiter, which is operationally the limit of mass of a planet, a gas giant, were going to be extremely rare. But conversely, at the low end, the number was rocketing high. And so even though the sensitivity limited us from detecting smaller planets, we essentially knew from this distribution they were out there. To use an analogy, if you're a fisherman and you had a net with 12-inch holes, not a very good net, you could only catch extremely large fish. Everything less than a foot in size would slip through your net. And so going fishing with a net like that, you would not be able to comment on the existence or abundance of small fish. If you make your net better with 1-inch holes, suddenly you're detecting all the 1-foot long fish and 2-foot long fish you caught originally, and also all fish larger than an inch. And of course, you'd find a lot of small fish compared to large fish, and so on. As exoplanet hunters improved their method, their instrumental technique gave them smaller holes in their net, and they started to see vast numbers of planets at the small end of the range. And that gave them confidence that as they continued to improve their methods, they would find yet larger numbers still. So to summarize what we know about the lower mass exoplanets, there are 2 categories. The distribution of masses or sizes is not smooth and uniform. It's actually got peaks. There's a peak in the exoplanet mass distribution around the size of mini-neptunes. These are small gas giants or gas dwarfs, and then a tail to higher masses, such that Jupiters and Saturns are actually quite rare out in the universe. And then there's a second peak around a few times the mass or size of the Earth, and these are called super-Earths. Over the years, hundreds of each of these types of planets have been found. And by making careful observations that net you both the mass and the size of the exoplanets, using the 2 available techniques for their detection, you can calculate a mean density. And the mean density is the first hint as to what the structure of these exoplanets is. Perhaps the most exciting category are the super-Earths, because they're cousins of the Earth, very likely with thin atmospheres, with geological activity because of their mass, and they're somewhat close in their situation to the Earth. Now, most of these, of course, have turned out to have orbits where their surface temperatures are very different from that of the Earth, and they're not habitable. But as time has gone on and hundreds of exoplanets have been discovered, we find planets that are closer and closer in their properties to the Earth we live on.